Okay, good afternoon, everybody. My name is Yanis Kutsu, and I will be giving the session this afternoon and the whole day tomorrow. This is this part of the training event is basically two parts. One is concerning cluster computing and scripting. And the other part is MPI, which we will mostly do tomorrow. You taking care of the admissions? I don't know why it shows it to me here. Yeah. So it's all rather introductory. So I don't assume you know anything about connecting to a cluster or MPI, but there is some C code involved here. Okay, so some familiarity. I mean, you won't have to write from the beginning any code yourselves, but we will see some code that you will, I guess, have to understand a bit in order to do the exercises. You can take photos of the slides, but you can also get them two ways. So there's a PDF of these slides on the GitHub. If you can also type this out into a browser, then you see an HTML version of these slides. So I'd encourage you to do that now, so that you can follow along. So this is what I said before. So there's two parts here in this session. So today I will begin this part. We see how far we get, but might need to continue some of this tomorrow. So just basic logging onto the system, moving around the file system. And we do some scripting by example. So I'll introduce an example that will require us to learn some scripting. And then submitting jobs, monitoring, etc. And then mostly tomorrow, as I said, will be MPI, which is the fairly standard way of writing parallel programs. Just to confirm, everybody's okay with if somebody tried to get the slides? It's working okay? Yes? Or at least nobody has problems. Okay, good. Yeah. Okay, so exercises, you don't have to do this now. I'll tell you when to do this, but the exercises are available for the 2 days on GitHub. So there's a common structure that I follow that I will explain. But they are also available on the system that we will use, and I'll explain when the time comes how to retrieve the exercises from the appropriate directory. Okay. So what we will be using for these exercises is the system that we call Cyclone, and this is sort of a very rough block diagram of what is involved here. You can think, I mean, the system is basically an interconnected set of so-called compute nodes. You can think of a compute node as basically everything you would assume is also inside maybe a desktop computer, right? Like a workstation. But of course it's smaller, so it fits on a rack, and is probably more powerful than what you would have in your typical desktop. So there's rows of these stacked up over in the computer room, and they're all interconnected with a special high-speed network to a so-called switch. And that switch then is also connected to some storage. And there are also so-called login nodes, okay? So we should distinguish here that login nodes are separate from so-called compute nodes. I'll say a bit more about that. There are 33 of these nodes in total, of these compute nodes. And they have these names. So there's 17 so-called CPU nodes and 16 GPU nodes. GPU nodes are nodes equipped with GPUs. And the ones that we will use today and tomorrow are CPU nodes. That's just the information of what these nodes include. So when you when we log into the cluster, which we will do in a few minutes, you actually end up on one of these login nodes, or sometimes you might hear them called front-end nodes. So I'll go back to this picture that I showed before. So here are these two login nodes. So these are just for basically where you land before you go to use one of the compute nodes, right? So there's, I mean, here I show two, but really there's only one in this system. Other systems might have more than one if they expect more users, right? So here we have just one of these. So when you log in, you end up here, and then from here, these login nodes are running some services, some resource managers, which sort of keep into account, right? Have a sort of keep track of which users are on the compute nodes, so that you can ask for access on the compute. So that's important to you to know, because to know that when you log into the system, what you're actually logging onto is not really one of the things that you should be using for computation, but there are some steps to do to actually get those compute nodes for you. So typically what you do is you log in, as I said, to one of these login nodes, and then from these login nodes, you ask for compute nodes to run your programs on. And we can distinguish between so-called interactive and batch jobs. So interactive means that as you are there, you actually get a compute node, you do what you do on the compute node, and then you log out. And then that's it. That's all the usage you've done of the compute node. But there are also ways where you can send a job to the compute nodes to run, a long job, which might take, a day or a week to run. Then you disconnect, you go home, or I don't know, you go to a seminar, and while you're at the seminar, the compute node is processing your jobs. Okay, so that's the distinction between interactive and batch jobs. And the software that is used to do this, to allow you to do this, so that that you request nodes from, and that keeps track of which users are using which nodes, is called Slurm in this case. That's the specific name, but the generic name is job scheduler. Okay, so there are many kinds of job schedulers. Here we have the job scheduler Slurm, which stands for, I don't know, Simple Linux Resource Manager or something. We will look at mostly these four commands: sq, salloc, batch, or sbatch, srun. We'll see what they do and how to use them. But just to say that maybe you're on a different system at some point and there's a different job scheduler, there will be similar commands to these ones, which just have different names, but they do the same thing basically. Okay, so this will be a very hands-on part of the training. So that means that you have to do things too, not just me. So we start with the first one, which is, I want to make sure, first of all, you can all log in somehow to the system. So if you registered as you should have, then you would be sent information of how to log in. If you if you're on Unix-based system or Linux-based system, then you should be able to open a terminal like I will do now. Put that up there. Bring in my terminal. Oh, no, come on. Sorry. Now, it's tiny. But I will make it larger. So here I am on my local machine, and the first thing I will do is, okay, you can ignore this junk that I'm putting at the beginning, but you want to run this command here, which is also on the slides, by replacing this with your username. And as I said, I want to make sure that you can all log in. And you see the nice message of the day. And you do add Cyclone. I don't know if France 01 works. Maybe it does. You should touch. I don't know. No, I mean, yeah, I don't know if that works. Maybe it does. Maybe it's the same thing, but yeah, but you don't know. If you don't know what any of that means, then just type this. Okay, and then when you log in, you should see this. Okay, I'll just make sure that everything can do that. When you create everybody online is okay. If anybody online has a problem, they should just speak up. Okay, then we give it a couple of minutes until everybody's at the same point. So. It work? Okay, good. All right. So. Okay, so as I was saying before, this drops you onto this login node or this front-end node, and you can see already from the prompt you get that you are on the front-end node. It says prompt 01 here, or you can type host name, which is equivalent. This tells you that now you're on front 01. Good, so this is the login node. And you can ask for one node. You can, so the first learn command we will learn is this salloc command. And if everything is set up correctly with the reservation and everything, then if you put this in, then you will get a node, or at least probably one of you will get a node because the reservation is only for one node. So whoever is fast enough will get this. Seems like I was faster than you guys. So I got node 5. It says so there, host name. It says CN05. Okay, so as I said, this is one of the 17 compute nodes. And now, because I want to be a nice citizen of the cluster, I will release it because I'm not doing anything with it. You can either type exit, or you can hold down Control and D, and that gets you out of the node. So see, so that's how we reserve a node and release a node. I'd like you all to try it a bit, just to make sure that you all have permissions to do so. You will try it once, but when you try it, then so they're either in 4 or 5, and it's the same slide as slide 8. Yes, and now unfortunately, okay, simple enough, right? Now, I want to just explain a bit what all these different options here that we put are. So minus big A is the project that you will charge. So this project is just a very temporary project that is only for the duration of these 3 days that we have the training. Okay. When you get a bigger project on the computer, then you get a different name, and that's the project that holds sort of your quota. And so you need to specify it to tell it that, so that the system checks that you have enough quota to run. This reservation command is not usually needed. This time we have a reservation, so we made sure that some nodes are free for us. And we, as this project edu17, can get these nodes if we use this option. But usually in a production system, you don't have special reservations for yourselves, right? So it's sort of it's work. There's an algorithm that makes sure that everybody that has time gets their equal share on the system. And minus P CPU, no equals, sorry, that shouldn't be equals there, just says that we request a node from the CPU partition. So that means we don't get one of those nodes with GPUs, right? So the system is split up into two partitions. One partition is the nodes that have only CPUs, and the other partition is the nodes with the GPUs. And here we're just specifying that we need CPU nodes. I told you to salloc and then log out immediately because we don't have a lot of nodes to use. But while you were on the node, of course, if you would type hostname, then you would get the host name of the node you were on. So here I say CN17. You would have seen CN05, which is the one. Okay, good. So yes, so we didn't wait for this. Release or control exit or control D would log you out of the node. And now, okay, so it's bad practice to use this salloc, okay? I mean, it's permitted and you can use it, but, you know, while you're on the node and not doing anything, you're not really using the node for any real computation. So when you use salloc, you might be blocking other users from getting on the node. If you have a project, a real project with computer time, then while you have the node allocated with salloc, then you are using your time, right? As time goes by. So we will be using srun instead of salloc. What is srun? Srun has the same syntax as salloc, but at the end you put a command you want to run on the node, right? And so srun is the same as doing salloc, running the command and exit, right? So it sort of combines these three, the workflow of these three commands. So if we use salloc in this case, if we use srun in this case, like this, it's the same thing I did before with salloc, but at the end I added this command hostname, right? This very simple command that just runs, it just tells me the hostname, I just put it at the end. And so now if you can try it, you can run this now, do it together. You see that you don't see much, but what's actually happening is it's doing a salloc, running hostname, exiting you. Okay, it's doing the three things that you did before in one go. And it's giving me the hostname, okay? Okay, so this way you don't hold the node for more time than you actually need to run whatever program you need to run. Good. Okay, and then, you know, the fact that we saw CN05 there, it just tells us that we allocated the fifth node. Good. Now, you can run multiple instances of this hostname in parallel, okay? So you can do something like what I wrote here, where I added this minus little n2 option. So if you do that, you get twice the host name. You see, CN05, CN05. And what happens is that, yes, of course. Where do you get the error? Here? Tell me what the error is. Maybe others also have the same error. So reservation takes 2 minus. The reservation is 2 minus. Then it should work. Okay. Good. Right, so you can do two like this, where minus big N1 here means use one node, and minus little n2 means you use two processes. So there's two processes, right, running on the same node, and these two processes, they're not doing much. They're just, they're just calling host name, but it's still something that's being run in parallel, right? And then you can, I think we don't have two nodes available to do this, but if we had two nodes, let me just try it, but I'm pretty sure we don't have two nodes today. Tomorrow we will have more nodes. But if yes, so it will say node configuration is not available because we don't have two nodes when we have one, but you could run minus big N2 saying, I want two nodes and I want two processes. And then you would see something like this. So one process will run on one node and the other process will run on the other node. And you can see that this is what's happening because you get two different host names here. Okay. So one run on the node with host name CN01 and one run on the host name with host names on the node with host name CN02.
Hello, can you hear me?
Yes.
So both of those processes are host name, right?
Both of those processes are host name. Yes, you are running host name twice in parallel. One instance running on one node and the other is running on one node. I see a lot of bubbles in the chat. Are you looking at the chat, or should I be worrying about the chat?
I'm currently trying to. Yeah, I'm looking at the chat in the moment.
Okay, thanks.
I try to use it to communicate.
Yeah, that's fine.
Why not?
So if you, Jakob, then since you're looking at it, then you just stop me if I need to stop.
Sure, I think there's a problem to connect actually to the machine, but I think this is
okay.
To figure out how to. Somehow the key is in the moment not connected, accepted. So if this is the case, one might have to contact the support. But let me first of all try again, and then let's see.
Okay.
If we can resolve.
I'll continue, and you stop me if I need to stop.
Yes, I will do.
Okay, now you can't do this again because we don't have two nodes today, but were you to do something like this, run on two nodes, one process, then it would complain that it cannot run one process on two nodes, and it would just run one. Okay, that's just so there's some edge cases there that are being taken care of for you by Slurm. Okay, now. Okay, so let's make this a bit more interesting. We've been running host names so far, and that's evidently a bit trivial. So, we're going to write our own program to run now. Okay, and so this is a good opportunity to also refresh a bit our Linux command line skills. So. Let's make a directory in our home directories, which is called NCC training, just so that we are a bit more organized, or at least seem organized. So so this creates a directory, this command, mkdir, NCC training. Okay. If I list now with ls, I should be able to see this. I have more, of course, directories here because this is not a new account, but if it's a new account for you, then you will probably only see NCC training. Then I want to change into that directory. So changing into the directory is cd, change directory cd, so cd NCC-training. So that I change change into it, CD NCC training. And you can see that the prompt has changed to show you that you are in a new directory, another directory now. And if you're ever lost, PWD will tell you where you are in the file system. The PWD stands for print working directory. So it prints the directory that you are currently sitting in. PWD tells you that you are under NVMe. H stands for home, then your username, and then NCC training, right? So your home directory is your home directory is your username. Basically, your username is used to set your home directory.
Jonas?
Yeah.
Yeah, I mean, it's still not working. Is there a possibility to have a breakout room or
A breakout room?
Can
you make that?
I have not
Yeah.
and in general, do you know if someone from the HPC, I mean, there was this Slack channel which we're opening, I think, so maybe we can try to ask there.
One we don't have for this one. Let me see if I can make one. I can make a breakout room now. Who do you need? Yourself and Yannis?
I guess so, yeah. I mean, we can try to. I mean,
Not me, right?
Okay.
Okay.
No. Okay.
okay, yeah.
I'll do that now.
Okay.
Okay.
Okay, we made our nice NCC training directory, and we're in the training directory. And okay, just to say a few things here. So the special directory / is called the root directory. Okay, it's the topmost directory. Okay? It's called the root directory. So everything starting with a / is called an absolute directory, because it's relative to the root. It's called an absolute directory. And everything that doesn't start with a / means it's relative to wherever you're sitting. Okay. Dot, the special directory, which is just a single dot, is an alias for the current directory. Okay. And dot is an alias for the directory immediately above. I'll show you some examples about this. And tilde is this wave, right? This tilde sign, which is usually found on the top left of your keyboard or left to the Z, is an alias of your home directory. So tilde is an alias of whatever user you're in as a home directory. Okay, well, that's very low, but for example, if you do something like CD, if you're here and you do something like CD .. that means go 2 directories up. Okay. And so now I'm outside of my home directory, 1 up, where everybody's home directory lives. So if I list here, I'll get a lot of home directories, right? So I went 2 up, so I got outside of my home directory. If I type PWD here, I see where I am. I'm in /NVMe/H, right? If I want to go back to my home directory, then there's a shortcut. CD with no arguments takes you back to your home directory. CD with no arguments takes you back. It's equivalent to CD tilde, right? Because tilde means your home directory. And PWD here, and you see we're under NVMe H and your host name and your username, sorry. Okay, let's go back to our NCC training directory. It should be still there, right? CD NCC-training. Okay, and because we'll be seeing multiple examples in this, let's organize a bit our NCC training directory into examples. So make a directory called 01, which stands for the first example, and then CD into it. Okay. So. What happened? Am I still sharing? I don't see the. Well, you sure? Yeah. Okay. Yes. Okay. Good. What did I say? Make directory 01, and then CD into it. Now we have a clean directory from where to do our next, our first exercise. Yes. So, okay. Now, this is the hard part. We need to write text files into this directory. Okay. You can use Vim or Emacs, or if you know how to do it with Visual Studio, connecting, you know, the fancy tricks you kids know these days, to do this from your laptops. Who doesn't know what I'm talking about? How to edit a text file? Okay. You do. Who does not know what to do here? We want to write a text file. You're all okay with this? Yes?
Could you maybe elaborate a little bit?
Right. So I'm gonna. Okay. So so this is empty, right? We want to write a program that a C program that will live in this directory, and there's many ways to do this. One way is to use a command line version of Emacs or Vim. So I want you to name the program prog-01.c. So this is how I would do it. I would, this means no window, so it just forces it to run in the terminal. So now I have an empty file which is called prog-01.c, and I can write text to it, right? This is not C code, of course, but I will write C code soon. But right now, I just have an empty file. You can do this with, as I said, you can do this with Emacs. If you're more comfortable with Vim, you can use Vim. What's it called? prog-01.c, right? And type it with Vim. Or if you've already done this before, there are ways where you can open a text editor here on your desktop and connect remotely and modify files on the remote system. So if you don't know, if you know what you're doing, then do what you know how to do. If you don't know, then follow my lead. Okay, so I will use Emacs to do this. So I again, as I said, I will run this command to make this program here, Emacs. So again, I have this empty file, and I want to write this program in it. Okay, so you can either, if you have the slides, you should copy paste this into the buffer here. Okay, that empty line there is inconsequential, but it just makes it prettier. And to save this file now, this file is not saved, and you think you can click on these edit file buffer, but you can't click on those. To save it, you need to use a shortcut, which is hold down Control and hit X without releasing Control, hit S again. Control X, Control S. And you see down here, it says wrote, and then the file name. Okay. The command Yeah, you hold down control, the control key, not the command key if you're on a Mac, just the control key. And then you hit X. And then without releasing control, or by holding down control again, you hit S. Control X, control F. And it should say wrote the file. Okay. No, it shouldn't exit. We're still there. It's fine. So here I just have on the slide, I have some comments about what the different lines in this code is. But maybe this is not very important up here, but let's just look at these few lines down here. So first I have a variable H name, which is just an array of 256 characters. So this variable is going to hold the host name of the node that I'll be running on, okay? And I also have another variable here, P, which I'm going to use to hold the process ID. And then I call two functions. One function is called getHostName. So this is just a C function that retrieves the host name in C, right? Not just this silly hostname command that we were running so far, but it's actually a library function that gives you the host name. And getPID returns an integer, which is the ID of the process that's currently running. And then I have just this simple print statement that just prints the host name and the process ID, and then the program returns, okay? Okay. So if you save it, then to exit, you use Control X and Control C. So the same way you did before, Control X, Control S. Now we do Control X, Control C, and we should be back to the command line. As you can see here, we're back at the command line. So we've exited the text editor Emacs. And if we type ls, we should be able to see our shiny new program here, prog01.c. This tilde thing is just a backup file that Emacs creates. You can ignore it. And there is a way to inspect the contents of the file without actually having to run Emacs every time. So if you use the command more, M-O-R-E, and the name of the file that you want to look into, then you just see the lines that you just hopefully put in and saved. If you didn't save the file, then you won't see anything in there, right? So this is a way, again, of inspecting the file without actually having to launch Emacs every time. So you see that it printed the contents of the file, and then you're back at the command line. Okay. So let me open it again, and then I'll repeat it. So hold down Control, and don't release Control. Hit X and C. First X and then C. Control X, Control C. Excuse me? You didn't save it before, so it's asking you whether you want to save it. Yeah. Okay, is everybody here? You're sure that you have a file now named prog01.c, which have these lines in it? I don't believe you, so I'm going to take it. Okay. So, right, you should be back at the, okay, I covered this. You should be back at the command line. And now it's time to compile this code. So far we have a text file. And if you're used to Python, that's all you need. You run, if this were a Python script, you run Python on it and it just processes line by line and it runs it. But C is a compiled language. All that means is there's a program that will look at this C file and output a binary program that then we can run, right? So we need to compile the source code into binary code, right? So we need to create a new file out of this text file that is machine readable and can run. So to do this, first we load this module. So you need to type into the terminal module load GOMPI, okay? This loads a common version of the compiler for all of us so that so that we're sure we're all using the same compiler.
Excuse me, sorry, I got a little left behind. How do you save the file?
Right, it's Control X, Control S. Hold down Control and hit X, and then hold down Control again and hit S.
Okay, thank you.
And then to exit, it's Control X, Control C.
Okay, thank you.
Good. Okay, so this is how you would compile the program. So first, the compiler name, this program that will parse the source code and make binary code is called GCC, the GNU C compiler. Okay. Then the name of your source code file, and then optionally you can add the name of the output that you want. So this is an optional option -O, which it just means name the resulting executable, the resulting binary file, name it P01. If you don't specify -O, it'll still work, but it defaults to the program that you create defaults to A.out. Okay, that's just what you will get. No, you don't need to. If you want to, you can. But you don't necessarily need to in Linux. So let me do this with you. Module, we said module load GOMPI. Oops, GOMPI, right? Good. And then GCC, the name of the program, -OP01 is what I decided to call it. All right. No output is good. It means that this has worked. And just to confirm, if I list the contents of the directory, then now I have an extra file, which is this P01. And depending on the terminal you're using, you might see it green, like I do, or you might not. If it's green, does it look like it's green? Yeah. If it's green because this has been marked as an executable program, okay? But now this is a program we can actually execute. And you can execute it by just typing // and the name of the program. Okay. /P01. And you can see the line that we put in our program, this printf statement at the end of the program. It says host name is front01, we're on the front end, right? Process ID is the 1025. You will all see different process IDs because every single new program that runs gets a new process ID, and the process IDs are reset when the system is rebooted. Okay. Okay, so I will take a walk to make sure that you're all here. Okay. All right. So I hope you're all here now. You ran this program that you. Yes.
I have a question.
Of course.
So it worked fine, but when I list the contents of my directory, there's a third file which has the same name as my text file with a squiggly line along with it.
This is if you use Emacs, you will see these all over the place. They are backup files. So Emacs saves backups of your
Okay.
puts a tilde at the end. You can disable it, or you can just choose to ignore it.
Okay, cool.
Yeah, but don't worry too much about that. Good. So we should be here now. Okay, I should say something now. So commands like, can you read that down there? Okay, commands like GCC or ls, these are programs exactly like the program P0 that you just created. Okay, but they are globally accessible, so they're accessible from any directory you're in, because your environment has been set up so that you don't need to provide the absolute path to the command ls every time you want to run ls. Okay, so it's in your shared environment, right? But this program P01 is not in your path. I mean, you just created it, right? So it's not in your path, and that's why when we run it, we put this / at the beginning, because it's to say to the system, I want you to run this P01, which is in the current directory. And by extension, that means that if you want to run it and you're not in this directory, so I just CD'd one directory up, and I want to run P01, then this will not work because it's not here, right? But I can run it by doing / the name of the directory within which it is, 01, and then P01, and now it will run it. Okay? Now, again, I'm just repeating what I said. ls is another program sitting somewhere in the system. You don't need to worry about where it is, but it is another program just like P01. It's just that I never need to tell the path to ls, because the environment has been set up so that ls is always visible whichever directory I'm in. Okay? That's just a long way that I explain why you need to put this / in front of P01. Okay. Now that we have our new program P01, we can run it with srun. Okay. So we don't use -big-N2. Again, we don't have more than one node in our reservation today. Tomorrow we will have more. So use the same thing, but with -big-N1. Okay, so I'm just going to copy this and paste it in the command line. And so now this is the same as we did before, but now instead of running hostname, we're running our own program, P01. Okay. And oops. Oh yeah. I forgot CD into 01. Okay. And okay, we get the same host name because this is running on the same node. But okay, but now maybe you believe me a bit more that we're actually running parallel processes, because each one is getting a new process ID. Okay, so these are processes being run in parallel. Okay, and you can go crazy and run, I don't know, 40 of these in parallel. You should get 48. No, 48 is too much. 40, let's say, should be okay. You should get 40 different PIDs on the screen, right? So these are 40 different processes running in parallel. They're not doing much, right? They're just calling a program that gets the host name and then gets the process ID and exits. So it's a very silly, simple program, but still it is a program running in parallel. Let me see. Yes, you made the same error. go back and do that once. I just want to say this again, that on the slides I have minus big N2, but unfortunately we only have, that means use 2 nodes, but unfortunately today we only have 1 node reserved under this reservation. And so this won't work. If this is the error that you get, I'll tell you what error you will get if you do this. You will see that it will say unable to allocate resources, requested node configurator is not available. Just put 1 instead of 2. If you had 2, you would see 2 nodes here. Now we only see the same node CN05 with a different process ID everywhere. Okay, I think we can take a short break now. About 15 minutes should be okay. And then how many? When does today end, Sergio? Oh, yeah. Okay, we continue tomorrow. Yeah. So we can take 15 minutes, so we can be back at 10 past 4, I guess it will be. Okay. Is this being shared? Okay. Yeah. There you go. Is it still sharing? Yeah. Okay. All right. So now we move on to a second example. So admittedly, what we've seen so far is a bit trivial. This program that just gets the host name, the process ID. We do something a bit more useful now that we know how to run programs in parallel. And so in step 2, we will write a simple program that will compute the number pi to some number of digits in parallel. Okay, so we'll use the parallel computation to get a more accurate number of digits on pi. First, I want to explain the process by which we will compute pi. Maybe you've seen this before, maybe not, but it's either case, it's fairly simple. So this is a very well-known example of how to calculate pi via so-called Monte Carlo integration, which is just a way of using the fact that we know that, for example, if you have a square like this one and you set the length of the square to be just 1 unit of 1 meter, 1 centimeter, doesn't matter. Then if you randomly hit points within this square, so these gray dots are just some random points that I put in the square, then the ones that are the ratio of the ones that are within the circle, within the shaded circle here, you can see it there, it's shaded. So if the ratio of the number of points that are within this quadrant of the circle to the total number of dots, as you increase the number of dots that you try, this approaches the ratio of the areas of the two shapes. So the ratio of the area of a quarter circle to the ratio to the area of the square. Now the area of the square is just 1, right? Because it's 1 by 1. And so you don't need to compute what that is. So that just tells you that the ratio of the points that are in the red shaded region to the points that are to the total number of points, I should say, reaches pi over 4, right? Because the area of the circle is pi r square and r is 1, so it should reach pi, and then this is a quarter of a circle, so it's pi over 4. Okay, and so the way practically you would do this is you would select a number between 0 and 1, right? Just choose a random number between 0 and 1, and you would call that your x coordinate, and then draw a new random number between 0 and 1, and you would call that your y coordinate. And thank goodness we know how to draw random numbers between uniform random numbers very well on computers. So then if you have the x coordinate and the y coordinate, it's very simple to know whether that coordinate is within the shaded red region or outside. It's basically this operation here. So if you add x squared to y squared and that sum is bigger than 1, then it means that this point lies outside of the circle, right? The most it can be is that both of these are 1. So it's 1 squared plus 1 squared. So that the biggest you can get is 2, right? That's because the maximum x can be is 1 and the maximum y can be is 1. If this is smaller than 1, then that means that you are somewhere in the shaded region, and then you can count this as one additional hit inside the red region. Okay? So you call n hit the number of times you are in the red region, and big N the total number of times, and then this n hit over big N should approach pi over 4. Okay, so yeah, this is a way to compute pi without actually calling any trigonometric functions. Like, we don't know what sinus or cosine or tangent is, right? We're just doing x squared plus y squared. That's the only operations we're doing. Okay, I don't expect you, of course, to write this program. So if you, so we'll copy it from somewhere where I've prepared it already. Just to stay a bit organized, why don't you do me a favor and CD to the top one directory up from where you should be now. Do this with you. So CD up, dot, dot, and make a directory 02. Oops, make dir. And then CD into that. Okay. Now I have a new, fresh, empty directory. And I want you to copy pi.c from this location here on the cluster. So basically, if you just copy this command, it should work. Okay. Let me see if everything is set up. Now I put it in a. What did I do with it? It's in scripting. I'm sorry, I changed it and didn't change the slide. Okay, I'll update the slides to the correct location. But for now, you just have to read it off my screen there. So it's Onyx data edu 17 04 scripting 02. Let's see. I'll wait so that I make sure that you all that you're all there. Okay, and then you do space dot to say that you want to put this in your current directory. Yes. No. Yes. No. No, it shouldn't. No quite. I'll explain. If you use the online version of the slides, then they should be updated to the correct path. If you're using the PDF, I can't do it right now immediately. So. Okay, but don't compile it and run. No, that's the wrong. No, that's the right path. That's the right. The HTML Okay, don't hide this now, as I said. I'm gonna look into it a bit with Emacs. So I do this and I do Emacs pi.c. Let's see what we have here. Yeah, maybe I do it like this because this has also nicer colors. So some header files there at the beginning, which I won't go into. But basically what we're doing here is we're setting this big N that I set to 10,000, okay? 10,000. And N hit is initialized to 0. So this N hit will keep count of how many are in this red shaded region, okay? So we draw a random number X and a random number Y. So this dround 48 is a C function that gives you a number between 0 and 1, random number between 0 and 1. Every time you call it, it gives you a different random number, okay? And then I'm checking what I said I should check in the previous slide, which is that X times X plus Y times Y. If it is smaller than 1, then that means I'm in the shaded region, and I increment this N hit plus plus is equivalent to take whatever N hit is and add 1 to it and store it back in N hit, okay? And then here at this line, I'm taking the ratio that I said I should take. This should go to pi over 4, so I multiply with 4 in front so that what I get ends up to be pi, okay? Any questions about what I'm doing here? Now, you might never have seen C before, but I think you understand that this is an iteration. It goes, you know, from 0 to n. Well, it goes from 0 to n minus 1, but that actually means n iterations.
I have a question.
Yes, please.
Before we mentioned that in Python we should avoid for loops because they're slow. So what's the difference between using a for loop here? Why is this efficient?
So in Python, you should use NumPy for the long for loops because NumPy is calling into a C function which does the for loop. Okay.
Okay, so NumPy and this is almost the same.
This should be as fast as NumPy. Yeah.
Okay, I see.
Faster. So I mean, somewhere there is a for loop, right? Written. Somebody wrote a for loop even for the NumPy function that you're calling, and that was probably written in C, if not Fortran. Maybe it was written in Fortran. But basically the NumPy functions are calling into lower level compiled code.
Okay, thank you.
Yeah, well, actually, maybe there's a more efficient way to do it than the way I'm doing it here. I'm not really concerned that much about making this be as fast as possible, to be honest. But your question was a good one nonetheless. I hope I answered it satisfactorily. What do I want to say anything here before no, okay. So I'll go back to the command line now. So now that we've seen what this does, we can compile it the same way we did before. So GCC, the name of the C file, pi.c, and then -o, and then a name we want to name it. And pi is just fine to name it like this. Okay. And then we can run it. like this, pi. It gives us a very bad estimate of pi because you need more iterations to get a right estimate of pi. Yeah. Yeah. Need to exit from the virus because the things you can change something, so we say that Anybody else need help? Any questions? No. Okay. So hopefully now you can all compile it with this GCC pi.c, put it a bit higher for the people in the room, and then run it once like this. And then if I go back to our slides, you can run, for example, on 4 processes. Okay, S run -n1 -n little n4, ask for the CPU partition, and ask for the reservation like we did so far. And we get 4 identical estimates of pi, which is useless. So what's the problem here? Well, I mean, some of you might already have realized that what's going on is, of course, all these 4 different processes are getting the same random numbers. So all we've achieved is to do this exactly the same thing 4 times. And so we're getting exactly the same estimate of pi. Now, what we want to do to have a truly parallel execution of pi is, of course, for process 1 to have 10,000 different n hits and have its estimate of pi. And we want process 2 to have a different 10,000 pairs of x and y's so that it finds another estimate of pi. And then the third one and the fourth one, etc., to have their own individual estimates of pi. So the random numbers have to be different within the 4 parallel running processes. But we haven't done anything to make them different, right? We're just running the same identical code on these 4. So what we need to do is initialize these random number generators that we're running with a different seed each time. And so we need a way to have a different thing, right? A different piece of data that will initialize a random number on each process. And so that's when we remember that in the previous exercise, we were getting this unique process ID from each parallel running process. So that unique process ID is a number that we can use to differentiate the different processes between each other and get a different stream of that random numbers on the first, second, third, and fourth, or how many other number of processes we will run. So that's exactly what I want you to do. We need to see the random number generator differently, and we can use this process ID from the previous example to see the random number generator. So all I want you to do is open the file with Emacs, now that you know how to open and save files, and add these 2 lines. This is just you only need to add these 2 lines, but you need to do it there, not somewhere else. Okay, so we get the process ID like we did in the previous example, and then we use this function srand48 with this p. Now this p will be different for each parallel running process, and therefore the stream of random numbers that will come out of the 4 parallel running processes will be different, and so we will get a different estimate of pi each time that we can then average over to get a better estimate of pi. So you need to do that. You need to save the file. You need to go back to the command line. You need to recompile the program, right? Because you changed the source code now. You need to recompile the program and then run it to convince yourselves that it actually gives you different estimates of pi each time. Bless you. I'll wait a few minutes until you go through that. Okay. So let me also do this. Map I.C. So I asked you to add the process ID equals get the ID here. And now that we have the process ID, we can seed the random number generator with srand and give it a value of the process ID. So before we weren't calling this srand, and all that meant was that the random number generator was being initialized with a 0, basically, every time. That's why you got the same random numbers many times as you ran it. So if I compile it now, then first thing I can check is that indeed, as I run it multiple times, I get different estimates of pi because there's a different PID every time I run this pi is getting a new PID from the system. Also, if I run it in parallel like before, I get 4 of these. And if I run it in parallel on 40, I should get 40 unique estimates of pi. Oops. Okay, that's all well and good, but now what do I do with these 40 numbers? It's good to realize that, you know, if this n was not 10,000, but was 4 times 10,000, 4,000, then that's just equivalent to what we did to running 10,000 in parallel, right? I mean, these random numbers are all independent from each other. So whether we run 20,000 all at once, or you run 10,000 on one process and 10,000 on another process, then when we add these together, it should be equivalent to having run 20,000, right? I mean, it's just how independent statistics work. So that means that any number of these estimates of pi that we have, if we average them, will give us a better estimate of this Monte Carlo estimate of pi. So we want a way so that we can average these 4 or 40 or how many hundreds or thousands of these parallel estimates of pi we're running. And there's not a unique way to do this, right? There's many ways you can write a Python script maybe to read the 4 lines and give you the result, or you can write you know, something else. I'm just going to use this a command line utility that will help me average these 4 or how many lines. But first of all, I'm going to run it like this. So this part of the command line is exactly as I did before, but now I put this little arrow, is this little greater sign, that says take the result of whatever is, you know, the output of this command and put it in a file which I name pi-out.txt. So I'm just putting the result in a file. If you run it like this, then right, so if I run it like this, then I should get no output, right? Before I got 4 lines, now I get 0 lines. The reason I get 0 lines is because I've put those 4 lines in pi-out.txt. I can look at it. I can do Emacs this file, but I don't need to modify it. I just want to look at it. So I can use more pi-out.txt, and I see 4 lines. Okay. Okay, now that I put it in a file, I can average it with a little utility that is very useful to know how to use, called awk, A-W-K, awk. This is available on any Linux, Unix-based system, and it just allows you to do things like operate on columns of data, right? It's just a simple utility. So I don't expect you to learn this command, right, in 10 minutes or 15 minutes or whatever. But this pattern here will do what we said we wanted to do. And I can explain some parts of it, although, as I said, I don't expect you to learn awk now, but it's useful to know that there are these utilities there, and then maybe you can Google an example and try to figure it out yourselves. Maybe now here I can just explain that. So the first part of this awk, maybe I should say, what we're doing is we're concatenating this file pi-out.txt. I didn't say what this cat command is, but you can just type it out and up to this point, and you see what it does. It's like more, okay? So it's the same as more. It just dumps it to the screen. Okay. Then what I'm going to do, this little vertical line now, it's not a slash, right? It's a vertical line. It's not an I. It's the character that is used usually above shift on many keyboards, not all, but it's the vertical line. So this means take the output of this command, so the output, and pass it through awk, but pass it in this specific way that I specify within these single quotes. So what am I doing? I have a custom variable, PySum. This is my variable as a user. I could have named it whatever I wanted. I decided to name it PySum. And what it's doing is it's doing plus equals $6. So I'm adding the contents of the 6th line of pyout.txt. And if you don't believe me, then we can count. So this is column 1. The equal sign is column 2. This is column 3. This is column 4. This is column 5. So the useful stuff is column 6. Okay, that's the stuff I want to sum. And so that's what this part is doing here. Right? So PySum plus, so this will process line by line and add whatever is in the 6th column to PySum. And then this end state, so this, whatever is here happens for every line, but whatever is after this end only happens at the end, after we finish the line. So after we finish all of the lines that I want to print PySum over NR, and NR is an internal variable which just counts the number of rows in the file, okay? So I didn't put 4 there because if I put 4, then this would only work if I had 4 lines in the file. I put NR, which adapts to how many lines are in the file so that I don't need to change it every time. Okay, so let me try this. So put the pipe there and fork, blah, blah, blah. And you see that it gave me this 3.1388, and you can maybe pull out your calculator and convince yourselves that this is indeed the average of these 4 numbers. But then hopefully, well, not hopefully, but we, wrote this in a very in a very general way where we, as I said before, we put NR here rather than the number explicitly the number, which means that this should also work now if I use any number of processes, so 40, for example. And if I do the same, then indeed I get, clearly this was divided by 40. If it wasn't, then I would get something that didn't look like 3.14, right? And just so you believe me, in pyout.txt, there should be 40 lines. And more than a page of lines. Okay, the last thing I want to, let me just say the last thing. So the last thing I want to do is maybe we don't want to need to remember every time all these commands. So maybe we want to put this in a script so that we have it for later use. So for that, we'll use a Slurm bash script. And if you go from where I said you can find py.c, you can also find a py.sh, okay? Let me copy this here. So I'll just do, so copy Onyx data edu 17 04 scripting 02 py.sh dot. Okay, so I'm going to copy the script here. And it's missing 2 lines, but I'll open it anyway to discuss it. So, so what you see here is a Slurm bash script, okay, where the commands that I put after srun, I've now put them in this in these sbatch directives at the top of the file, okay? So some of these you remember that we put on the command line. So the -m is the number of processes. So now instead of having to put that in the srun command, we can just put them here and we don't need them in the srun command. So the reservation is there. The project is there. The partition is there, but there are also some additional options that we haven't talked about so far, okay? So one of them is this -j, and this is just the name of your job, okay? It's just naming the job something. And then you have the -o and the -e, and that is, so now we're going to run this program not interactively, but in a batch script, which means that we can submit this, disconnect, go away, and this might run without us being in front of our computer. So we need a place where the output of the different commands should go. And that is specified here. So you have one file for the output and one file for any errors, okay? That's specified with a -o and a -e. Another thing we're specifying here that I didn't talk about so far is a time limit. So we're setting a time limit to the program. We're saying that if it runs for more than 2 minutes, then kill it. Maybe something went wrong and it's stuck. So that's what this -t means. Okay, but up to here, this script is not doing anything, right? It's just initializing. So I want you to add these 2 lines at the end. And these are basically the 2 lines that we were running on the command line, one after the other, in order to get the average of pi. So if you put those 2 lines in the scripts, so you Emacs the script, right? You put those 2 lines, then you see that the srun does not need any options now, because all the options have been specified at the top for srun, okay? And that's just what I said, -j sets the name, -o, -e, -t. Okay, I'll leave this on the screen so that you finish it. But it's also on the slides. This is slide 21. Okay, when you add those 2 lines to the script, then you're ready to go. So what you do is sbatch pi.sh, and this sbatch submits this script. It doesn't run it, okay? It just sends it to the scheduler. It might run now, it might run tomorrow, it might run in a month if you're very unlucky. But just because this sbatch command returns does not mean that your script has been run. It just means that it's been sent to the queue, okay? And I'll show you what I mean. Well, first of all, I have to add these 2 lines. So add this line, and I will add this line. And then I'll go save again, get out of Emacs, and I will type sbatch pi.sh. It's, yeah, okay, because I asked for 2 notes. Okay. Right, if you ask for 2 notes, you get this problem because we only have 1 reserved today. I'll change it to 1. Batch. Okay, you say, is he submitted batch job? Now I can check the queue. Okay, this program is very fast, so it runs immediately, but right, if you use SQ, if you do it fast enough so that the program does not complete, then you will see something like this. So job ID, partition, name of the program. This is the character that the name that we put after this big -j. then you see that the user that's running it, and then a status. Okay. If the status is R, it means that the job is actually running. Okay. This runs very quickly, so it's unlikely that you will see the R. And then the other things you might see is PD, which means it's not yet run, it's pending, like you see up here. Or you might see CG, like I saw when I run it, which means completing. So it's finished, but it's stuck there for a few minutes until it finalizes and releases the node. Okay, and so when you run it, then hopefully in pyout.txt now you get the 40 lines, because it's the same as before. Remember, what we're doing in the script is we're running it like we did and putting the output in pyout.txt. But this line, when we did it interactively, we saw it on the screen, right? So where is it now? Where? It's whatever we specified here with a -o. Okay, so that's where you'll find it, and we specified py.txt. So there should be a new file, py.txt, which has the average result in it. And indeed, there it is. Okay. Okay. That's actually all I wanted to say for today. Tomorrow we continue with some MPI. A bit more heavy stuff than this, if you found this a bit boring. Any questions? Yeah. No, it should still no. But if you copied it as I have it, then if you have -2 here, and this to 40, because if it's 80, it still won't work. Yeah. With Emacs? Yes? Oh. If you want to change the -2. Okay, no, because you need to go to the other. Because they need to do that. You need to go to the other. Yeah. Now, because it's still in the terminal, you can't report the mouse. You need to incorporate that. So you need to put CP in front. Yeah. And at the end, you need to say where to copy dot. So you put the arrow up, bring it back, space. Now you can, so you're saying copy from to. So now here there should be a private stage. What is it? Yes.
Unless there's another question, then we can end today's session and reconvene tomorrow at 9:55.
Will they, the recordings be uploaded?
When they've been encoded, yes, it will be available, yes. Today, ideally.
Oh, okay, okay. Is there a link?
They're on the event website. So you've received the email with the schedule. It should be on that page.
Okay, thank you.
Okay, so goodbye everyone for today, and we'll talk again tomorrow.
Yeah, bye bye.
Goodbye.